Hello, my name is Marcus Kitty Kit. This is the final and last assignment for Comp 3132, also known as Machine Learning. And for this assignment, we are given a task. So, right here, the document says that I must implement all the techniques I learned from this course so far. And these topics should include data preparation, the train validation and test set splits, L1, L2, or dropout, over parameterization, right? Data augmentation, covenants, and number of epochs required for acceptable matrix. And for this data, I can choose any data set online. It can be from this data, Kira's data set, or data quest. And for this data set, I chose the MINT NNIST data set, which is a data set consisting of numbers from 1 to 9 or 0 to 9. So, and it is part of the Kira's data set. So, yeah, it's a valid data set online that I'm going to use for this assignment. So, first, the data preparation. What must you do first if you for your machine learning model? First, you must prepare the data. For data preparation, import the libraries. You load the data, right? And I'm not going to bother to run like the training or run these lines of code, because if I do, it's going to take a very long time. It's going to take a long time. And that's why it's best to, if I recorded this after running this Python file. Yeah. But we need to, but first, before we're creating a model, you need to understand what kind of data set we're dealing. And the way to understand the data set, you can use dot shape, and you can print and put in a print statement. So in this dot shape, it shows the length of the data set. So this is let's say 60,000, right? You can print the X train, X test, Y train, Y test, right? So you have 60,000 data files for training and testing, 10,000 testing files, right? That's how it is. And of course, we can visualize the data using matplotlib, right? We can also use NumPy, Pandas, or any of these Keras data sets, like mints over here, sequential, dance, drop, and flatten, and etc. So it's best to visualize the data. And what number is this? It's 5. And this one is 7. So again, Mint's dataset is just a series of numbers from 0 to 9, right? And you can see it's just numbers and not something like cats and dogs or clothing like jackets and trousers. But yeah. And after data preparation, it's now time, and understanding the data and visualizing the data set, it's now time to define a model. I have 3 models here, right? This is your standard model, right? So we have a sequential model, right? I added some layers with max pooling, flatten it, and then some dense layers, right? Compile them. After that, once you define the model, you have to compile the model, and you have to choose your optimizer, your loss, and your metrics. And after compiling the model, it's best to, I recommend summarizing the model, because you get to see the layers, the types, the output shape, and the parameters, right? It's just more information for you to gather on what kind of model you are creating, right? And after that, now it's time to train the model. You can just model.fit, but I think for practice and industry standards, it's best to define a history variable and then equal that to the fit. And as you can see, you can have a batch size, you can have the number of epochs, your verbose, and your validation data. So I chose 10 epochs. I ran it. This took me 3 minutes because if it's more, it's going to take longer. And we have the evaluation test data. Now we can, after that, evaluate your test and training data. So we have a test loss of 0.49 and a test accuracy of 0.867. And for the training data, it's 0.51 and 0.8618, etc. Right? So how do I know? And based on this evaluation, and you can also visualize it in a plot in a graph, right? This model is overfitting. I mean underfitting. And why is that? Because it's too simple. So over here, if you visualize it, right, you can see that the training data, the model is following the accuracy pretty well in the beginning, and then it slowly uh steeps closer and then almost intersect, steeps closer to the test accuracy. So don't get me wrong, this is an okay model, but when you have something that when you're dealing with like when you're dealing with predictions that are just too complex, too 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 complex for a model to understand, then yeah, when you have a simple data set, it's gonna have a high bias because, for example, when you're underfitting, you're going to have high error rates on both the training and testing. And the model fails to capture the complexity of the data. And you're going to have, and this model is going to make a very biased prediction on on data on data sets and even like, for example, other topics, right? And what causes underfitting? Well, the what there are several points that I will list and that causes underfitting. One of them is that I probably one of them is that where I'm using there's not enough training data when I created the model. It could be incorrect hyperparameters, right? It could be the amount of epochs that I created, that I tested it or trained the model on. And because of that, the model looks like this, where look, it does well, like it generalizes well in the very beginning, and then slowly goes very close to each other. So it's not a terrible model, but it's a very simple model. That's is essentially underfitting. And here is another model. I create a second one, and this time it's where, and it's almost similar, but it's going to be overfitting. So how am I overfitting? Well, it's the same thing, right? But double the parameters, so double the density layer, right? I also use a different optimizer for this to compile the model, and of course I have more epochs, which is 20, and after that, yeah, this took almost 20 minutes. And when we evaluate the data, as you can see, the accuracy, the test and training accuracy is 99%. What does that mean? And if you visualize it on a graph, it looks like this. Now, what does this mean? This means that this model is overfitting. And what happens when you overfit? Well, it means that the model learns the training data too well, and that includes noise and irrelevant details and performs poorly on a new data. So, for example, what I mean by this is like, if you have this is underfitting, right? you use a linear model. When you have a bunch of data that is scattered in an almost quadratic line, the linear model is not going to capture everything because it's too simple, and you're going to have very inaccurate and very biased predictions using underfitted model. And when you have an overfitting model, it's going to capture every single training data, right? And it's going to be too complex. When you have too many training data, right? You're going to have a very high variance of of different different data points in the data set where it captures every single irrelevant point, and it's not going to generalize well. And we don't want a model that doesn't generalize too well, as you can see by this graph. So in the training set, it goes up, and then there's a huge gap, and then that's it. That means it's overfitted. And how do you reduce overfitting? There are several ways. You can use dropout, you can use L2 regularization, or you can use data augmentation. These three uh, these three techniques are ways of reducing overfitting. And when I run it, right, as you can see, it took me 60 minutes, right? Same thing, but I defined a data augmentation. I I included a dropout layer, and yeah, and the same thing this time. A test accuracy and a test loss is not too it's not too much. And this is a very good model. Why? It's because it's not overfitting, it generalizes well, it's also not a simple model. When you have this is what a model should be. No, it doesn't overfit, it doesn't underfit. It's a model that generalizes well with unseen data, or with the both training and testing data. So that way, when you're making predictions with this model, right, you are going to get way more accurate predictions compared to an overfitting model and an underfitting. And how does dropout how do these three techniques reduce overfitting? Well, a dropout layer randomly drops units during the training to prevent the model from relying too much on any specific neurons, which is the one where I showed you, right? And L2 regularization penalizes large weights and encourages the model to keep things simple and less prone to overfit. And data augmentation expands the training data artificially, helping the model generalize better by seeing more varied examples. And that's it. That's how you reduce overfitting in your model, in your machine learning model. And I forgot to mention, you can also define, what's it called? You can also use train test split. You can use train test split when you're instead of using the standard Keras model. So yeah, it's just, and over parameterization just increases. It's just helps your model make have more learnable parameters. So yeah, that's it for this video. Thank you for watching. Have a good